people who say, okay, you believe in the block universe, and in a certain sense, I do. They say, oh, that's static. And I say, what do you mean it's static? I mean, the word static in English, or stationary, or frozen, or fixed, refers to things that persist through time and fail to change as they do so, right? In other words, being static only applies to things that persist through time. Just as changing only applies to things that persist through time. A single event can neither be static nor change because it doesn't persist through time. Now, does the block universe persist through time? Well, no, as I say, it's not in time. Time is in it, right? So it's neither correct to say it's changing, nor is it correct to say it is static. It contains all change, right? It also contains everything that happens to be static. But without putting the whole of space-time into yet a hypertime or something, you couldn't even ask a question like, is it static or changing? And we don't need a second-order time. The only time we need is the one in the block.
Hello, my geeslings. This is Mother Goose Robinson Earhart here with the introduction to Robinson's podcast, number 115. And this episode is with two previous guests of the Robinson's podcast, Multiverse, and they are Craig Callender, who is professor of philosophy and co-director of the Institute for Practical Ethics at UC San Diego, and Tim Maudlin, who is professor of philosophy at NYU and director of the John Bell Institute, which we will get back to momentarily. But Craig and Tim are both leading philosophers of science and physics. As I mentioned, Craig also appeared on episode 73, where we talked about pseudoscience and conspiracy theories, and that was very fun. And then Tim was a guest on episode 46, which covered laws of nature, absolute space versus relative space, and free will. And then he was also on episode 67 with David Albert, which was totally awesome and all about the foundations of quantum mechanics. But in this episode, Craig, Tim, and we delve into the philosophy of time, which has been a focus of both of their research for a long time. And we start with McTaggart's A and B series of time, and we touch on the reality of the past, the present, and future, respectively, the direction of time, its relationship to relativity and quantum mechanics, and time travel, and a little bit of time travel movies. But as I mentioned, Craig and Tim have both written a lot on time, and you can check out their books on the subject. And if you're interested in the foundations of physics, which you absolutely should be, then please check out the John Bell Institute for the Foundations of Physics, which is devoted to providing a home for research and education in this important area. As I mentioned, Tim is the director of the John Bell Institute, and I couldn't ask you to donate if I hadn't myself, and I just donated because the work Tim, David Albert, Craig, Barry Lower, Sean Carroll, all previous guests and others, Hugh Price, probably other people I'm missing too, are doing tremendous work in the foundations of physics. And it's very important to me because it's just about the most interesting topic I can really think of. And I suppose then it's also very important to the show as well. So I'm very much invested in the John Bell Institute for the show, or on the show's behalf as well. So at this early stage, any donations are immensely helpful. And you can find the John Bell Institute quite easily just with Google. It's also available, or you'll find it through Tim's website at tim-maudlin.site. And then you should also keep up with Craig at craigcallender.com. So now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Craig and Tim. I'd like to begin with some really basic questions about the metaphysics of time, just to get us started. And Craig, since I know you've written about this, Not that recently now, since your book, What Makes Time Special, came out in 2017 now. But I thought we should start with McTaggart and his A and B series of time. And can you just walk me or us, my listeners, I mean, Tim doesn't need this, through just what this is?
Sure. So McTaggart was a Scottish philosopher. Interestingly, his middle name was also McTaggart. So he was John Ellis McTaggart. And in 1908, he published this paper, which then really was a big kind of hit in philosophy of time, or maybe even started what we might think of as kind of analytic philosophy's take on the metaphysics of time. And he distinguishes a bunch of different ways you can think about time. And so you can think about time as, if we think about a sequence of moments, and so we're not thinking about relativity or anything. If we think of a sequence of moments, you could order them with a betweenness relation, say which ones are between one another. You could order them. You could say which ones are earlier than other ones. And so if you order them all by the earlier than relation, then you get what McTaggart called the B series. Now, if you then ordered them a different way with these so that's all sort of a bunch of relations, just looking at all the different relations between the different moments. But if you used a different sort of vocabulary, you could order them a different way. And so you could order them in terms of past, present, and future. And so in cognitive linguistics, this would be called a deictic structure. And so this makes reference to a special now, or deictic center. And so you could order everything in terms of past, present, and future. And you can see there's a kind of difference because, what's now is indexical. And so it might, depending on when you say it, different events might be past, present, or future. Whereas, Socrates drinking hemlock is always before Socrates' death. No matter, it was before that event happened, when it was in the past, when it was in the future, when it was present, when it was now in the past. And so the truth value of the A theoretic properties, past, present, and future, sort of change with when the utterance is. Whereas with the B theory, that's sort of timeless. Now, the way I think about it is that one is I think so McTaggart then used this distinction, and he said that he made this famous argument that time is ideal, and he argued that all events had to have both A properties and B properties, and if they didn't have A properties, it wasn't really time. And then he kind of tries to show incoherence. But to me, I guess the lasting thing of interest there is really that we human beings and probably animals too do carve up the world in this atheoretic structure. Use this deictic structure, and so my book I call it Manifest Time, and try to get away from all the kind of A versus B stuff. But it is still very important to the way we think about time. So we do carve it up into past, present, and future. We tend to attribute different properties to them, so we don't think of the past as something we can change. There's no button I can wiggle that will change where I was born. We tend to think of the future as open, ripe with possibility. And then we think of that tripartite structure of past, present, and future as updating and changing. And so, I call that the flow of time, but that's like the least clear phrase in philosophy, really, because so many people mean different things by it. But I just think of this kind of updating deictic structure. Yeah, so then when you get into the metaphysics, so none of that has anything to do with metaphysics, really. That's just sort of different concepts we use when we talk about time. But then, a lot of metaphysicians then said, we must find a metaphysics that respects the atheoretic structure. And so then there are presentists and don't know what the right word is, becomingists, possibilists, who then craft a kind of metaphysics. There's really like, just dozens and dozens and dozens of these views, almost as many as there are analytic metaphysicians of time. And then, that's usually contrasted with then the so-called B theorists, who sometimes called the block theory. And then, historically, there's been this kind of dispute between the two camps. I myself am not actually 100% enough of a metaphysician to even think that the two camps are two camps, that they might actually just be the same camp, really, the two different ways of speaking.
Yeah, can I actually just jump here? I mean, I think Craig is giving a perfectly accurate historical summary of how a lot of this has been taken, or the labels people have stuck on themselves and on their opponents. But I think there are some things worth pointing out. I mean, the first thing worth pointing out is that as far as McTaggart goes, he wasn't A versus B at all. The structure of his argument is the A series, he claimed, is incoherent, and the B series presupposes the A series, ergo the B series is incoherent, right? He wasn't pumping for one. And then you've got to drop down to the C series, which very few people talk about, which is the first one that just to lay out all the events in the universe and only order them by betweenness. So there's no asymmetric structure there, right? Because if B is between A and C, then equally B is between C and A. And the idea that there are two different things, A and B, I mean, there's the linguistic resource you get when you have deixis. That is an indexical. That is a token reflexive thing, like here or now. To make the analogy, you have a map of the United States, and you can kind of look at the map and notice just from the map that this town is near that town. But if someone just asks at a certain moment, gee, is such and such a town near? What we do is we fill that in, that's with here, which is an indexical, right? Is it near the place where I am right now? And then from the map, you can tell, right? You haven't really added anything. You haven't added anything to geography, right? You haven't added anything to reality. You have some token reflexive indexical linguistic things. Given the B series and an indexical, I'll give you an A series. And if the indexical sticks down at a different point, it'll give me a different A series. That is, relative to Socrates' death, certain other events were near in the future, to the near future, and some to the near past, like his trial. Right now, his trial is pretty far in the past, as is his death. None of this is puzzling, right? None of that is odd. None of that should require any much thought at all. The real question is there a fundamental asymmetric before and after relation in terms of which we distinguish the past direction from the future direction, and therefore, at any given moment, the future of that moment from the past of that moment? The C series kinds of denies that. That strikes me as being quite odd. I don't think there's actually anything in physics that suggests that.
Yeah, I agree with you about the A and the B are complementary, and it's just really about indexicals. And their only mystery is why the heck philosophy went for like 40 or 50 years thinking that the main argument was trying to reduce the A. So the game was for a long time was, can you say atheoretic stuff using only the resources of the B theory? And, that's a mug's game, because you can't do that with personal pronouns. You can't do that with spatial here. You can't do that with anything. And so you're going to lose if you try to play that game. But that doesn't mean you lost in any way, because you shouldn't have been playing that game.
So just to make sure that I'm following completely. So are the A theory and B theory, they're not really metaphysically loaded, but just concerned with how we conceive of time, and then the further, more metaphysically committed categories. I think, Craig, you mentioned presentism, and where only the present is real, and then possibilism, where the past and present are real, and then I don't think you mentioned eternalism, but where all three are real in some sense. These categories are just layered over the A theory, the B theory, and the C theory, depending on which, if any, we adopt.
Yeah, that's the way it's typically taken.
Yeah, can I just just linguistically make a comment here? McTaggart doesn't use the terms A theory and B theory. He uses the terms A series and B series. The B series is all the events that ever have happened, are happening, or will happen, laid out with a earlier later relation on them. Presumably also with the distance, like how much time, but he doesn't really talk about that. At an A series, there's only one B series. There's only one, okay? An A series is all the events that ever happen laid out with one of them indicated as now, some indicated as to the near future of now, some to the distant future, some to the near past, and some to the distant past. So you just take the B series and stick a pin in it somewhere, and it'll give you an A series. And if you stick the pin somewhere else, it'll give you a different A series. Those aren't two different theories, right? They're just not. I mean, they're not theories of anything. They're just series. The reason that McTaggart thinks he can get a contradiction out of the A series is because he calls it the A series as if there's only one of them, when obviously there are infinitely many of them. You just stick the pin in any of infinitely many different places and you get a different A series. So if you mess that up and think there's only one of them, then it's not too surprising you can get contradictions.
Yeah, Tim's right that, it's interesting to look at the history of where did the eight properties end up becoming the eighth theory. And then, somewhere in my book, I've got a kind of canonical statement from the 1960s or something of the eighth theory. And I point out that it's got there was like 3 or 4 claims. One was, there was like 1 or 2 semantic, 1 or 2, metaphysical, and 1 or 2 epistemic. And it was this kind of weird grab bag of theses that people psychologically associated with one another, but they were completely logically detachable.
And now, Craig, in our correspondence, you mentioned that you thought that Tim sometimes sounds like an A theorist, yet you think he's a B theorist. And I was wondering why that is, and how this relates to whether there is an objective now, and how Tim feels about this.
So, in some of Tim's writings on time, Tim's a great philosopher, and he's also rhetorically gifted. And so there are these rhetorical flourishes of, motivating his views on time. And sometimes I think he dips his toes into the kind of atheoretic intuitions to try to motivate his view. I don't know. Do you recognize that in yourself, Tim? Or
well, as I just said, I don't recognize the difference between the A theory and the B theory. So I wouldn't recognize an intuition as being either A or B. I see the difference. Let me actually just state, I was just talking to some other people here in Lugano about this. Here are 2 questions that are just yes, no, clear questions people can disagree on. One is there a universal moment, such a thing like a universal moment of time, the way Newton thought there was, what we call absolute simultaneity, or an objective foliation of space-time, okay? And we can explain, if you want, Craig or I could explain what that is, but you can just ask, do you believe in that? That's a question. Here's another question. Is there a fundamental temporal asymmetry between the future direction and the past direction? The C theory really denies that, and both the A and B series presuppose it. Those questions I understand, but I don't see a difference between A and B. So if you tell me I'm using A intuitions to promote what's really a B theory, I honestly don't understand what you're accusing me of. Because I say over and over again, give me a B series, I'll give you as many A series as you like. Give me an A series and I'll extract the B series from it. I don't see these as competing. So I'm not quite sure what the accusation is, right?
Yeah. Well, yeah. So, we agree. Well, yeah. So maybe I should point out for viewers. I think Tim and I are pretty, in the 1% of philosophers who agree on this point that the A and the B are really just not at odds, but are just sort of two ways of describing the same reality. So probably most people in philosophy would disagree with us. So we agree on that. Yeah. And so then, well, I was just thinking, I don't know, I don't have a passage in front of me or something, but the kind of flow of time talk, if it sort of goes into, if it sort of dips into, and probably you don't do this maybe, but like existence talk, where the past exists and the future doesn't exist or something.
Yeah, I don't say that. I absolutely don't say that. I think the future, there was exactly one past and there will be exactly one future, and that the totality of all reality is that unique past and the unique present and the unique future. And I don't see I don't see a metaphysical difference between those.
Oh yeah. Well, so then that's interesting, because that's what I thought you thought, but I was I was curious though.
Well, I mean, Tim, what you just said raises my next question, in that, are there logical grounds, I mean, prior to physics, for holding that any one of presentism, possibilism, or eternalism is preferable or more probable than any of the others, or that rules any out, before we ask whether current physics is more sympathetic to one or another? What I'm hearing you say is that if there is one past, there will be one future, that you sound like an eternalist in some sense, but maybe
if you want to call it that. I mean, I don't, that just don't say, people say that and then they say, oh, there's a block and there's no motion, or change is an illusion, or stuff like that. That just doesn't follow at all from anything I just said. You just named three things. I guess if my choice was eternalism, presentism, or possibilism, I'd go, yeah, I'm an eternalist for the reasons I just gave. What's wrong with presentism? I mean, possibilism, you're going to have to describe to me, because I'm not quite sure I quite understand even what it is. What's wrong with presentism? Well, first of all, usually to even state presentism, you certainly do need this kind of preferred foliation thing, at least as I understand it. So you say there's something like all the stuff that exists right now. And that is supposed to pick out something. And then you say, and that's all there is. And then you say, but gee, don't you think it's true that, say, there were dinosaurs, or don't you think maybe, let me use another example. Don't you think it's true that Socrates had a particular blood, right? He was O or A or B or AB. He was something, right? We don't know what it is. We'll never know what he was. There are no retrievable records that you could ever find that will settle that question. Nonetheless, there's a fact about it, right? You say, well, what makes that a fact? I would say stuff about the past. Now, the presentist doesn't have any stuff about the past in that same way. So it looks like the presentist is forced to say, well, if there's any fact at all about Socrates' blood type, it has something to do with what's going on right now. And since we can't find anything going on right now that seems to settle that issue, it looks like you're stuck with saying Socrates didn't have a blood type or something like that, which just seems lunatic to me. I mean, is that a logical objection? It's more a sanity objection. Of course he had a blood type. I mean, he existed. But what are you talking about? And the facts that make it true that he had a certain blood type are facts about the past. So if you have a theory that denies there are, in some sense, facts about the past, or they have to be reconstructed as facts about the present, I just don't, what are you doing? And why are you doing it? I mean, I'm puzzled.
Yeah, it's really hard to see how you get a debate going. Yeah, so imagine I'm a block theorist and I say, earlier there were dinosaurs, and now the presentist comes along and says, no. Pastness adheres to dinosaurs. And then I say, well, aren't you just using a kind of temporal operator that, kind of one-to-one mapping with my earlier than relation? And yeah, so then
And you might wonder, what are these dinosaurs it's supposed to adhere to anyway? I'm not sure that the present is
yeah, and then
dinosaurs
to answer your question,
errors of pastness, do they?
that's right. So then, but now the dinosaurs don't exist. Well, and then I'll say, well, they don't exist now. So we're just fighting about the scope of the existential quantifier. One of them opens it up, one of them shrinks it to a slice, back and forth. But then if you say, well, there is a difference between, that in the past, there were dinosaurs, but there weren't unicorns. What's the difference there? And suddenly they have to make there be all these kind of weird facts so they can make what you just said, Tim, true, that there were dinosaurs. But now all those facts are starting to like fill up the block, and it becomes very kind of block-like, and so then you start thinking, well,
and institutional facts don't look like physical facts anymore, right? If you're just filling up the past regions of space-time, you're filling it up with what? With atoms and electrons and all the stuff we think that exists. But if you're filling up the present with ghosty, weird metafacts that make claims about the past true, even though, I don't know, I find it very hard to take that stuff kind of.
I think in some ways, I have actually a kind of cynical sociological theory that maybe I shouldn't say, but really it's like the perfect way for metaphysics to inoculate itself, or to make it so that it's not inoculate itself, to make itself so that it can't be tested by science in any way, or be relevant to science, because you've now picked the perfect property or a predicate to use, existence. Is the only thing that differs between the theories is about what exists as of when, but existence doesn't have it doesn't smell, it doesn't have any color, it doesn't have anything. It doesn't enter into the network, the causal network of things, and therefore you can't explain anything, which is my ultimate complaint about it. Because I think the idea is that presentism will explain why I think that there's the now is distinguished or something like that. But just by saying it exists, that doesn't connect it in any way to anything where I can explain why I have the intuitions I have.
Tim, I'm a bit perplexed about why you see the future as being equally real as the past. And that, as you've already mentioned, we have facts about the past, where we know facts about the past. The present was, in a sense, caused by the past. And it just, in general, seems determined in a way that the future isn't. And I can understand why one might think that there could only be one possible future, or there will only be one future.
There's only one actual future.
Right. Without one thinking the future is...
this whole one actual future.
What I'm saying is that one can accept that there will be only one actual future without thinking of the future as being real in the same way that the past is.
Well, I'm just a little puzzled what the view. Look, there's the phrase attributable to the great philosopher Doris Day, "Que sera, sera," which strikes me as just a triviality and not a deep metaphysical principle, right? A bunch of stuff is going to happen. What makes it true that this will happen rather than that will happen? Well, stuff that's yet to happen. It's the future that is going to, as it were, be the truth maker of claims about the future, just as it's the past that's the truth maker of claims about the past, like in the case of Socrates' blood type. So I'm not quite sure. Of course, there are differences in epistemic access. That's just a fact. We know different things about the past and the future, right? I know the weather in the past 7 days in Lugano a heck of a lot better than I know what it's going to be for the next 7 days. That is an interesting asymmetry and one worthy of some consideration to explain. And I think lots of relevant work has been done to explain it in terms of statistical mechanics and various things. But suppose some people think if you go back kind of to the Big Bang, you can go back earlier than that there's an earlier epoch right? Cosmological epic. And this is a view that, say, Roger Penrose has. And it may very well be that that's true. And it may very well be that because of the Big Bang and all this kind of very hot mess in between, our epistemic access to the previous epoch is nil or nearly nil. Would that make it any less real? Not in a bit. Not even slightly less, right? Why does my epistemic access to it have anything at all to do with its reality? I just don't see the connection. So maybe you can explain it to me. Epistemology and metaphysics are just different disciplines. They're engaged in different questions. And, one of the big mistakes of logical positivism was to kind of try and reduce metaphysics to epistemology somehow. And we all know how that came out. It's not a happy story. So in what sense, at one point, David Lewis says, look, people in the Middle Ages who died of cancer, their suffering was just as real, right? Just as real as people today in hospitals. Well, probably more intense, but anyway, just as real. And people who suffer from cancer in 30 years, they're suffering just as real. In some moral, right, evaluation of goodness and badness, nobody gets extra points for where they sit on that timeline, or fewer points. So I'm not sure, what is the intuition I'm supposed to be? What's the strange intuition in thinking there will be a future?
Well,
exactly.
Yeah, I lack the sophisticated vocabulary to make it clear, and perhaps it's just because it isn't clear. But I think what I have something in mind is a four-dimensionalist view where I'm just like a big worm. We're all just big four-dimensional worms, and my past parts, the things that have already elapsed, seem to me in this view in which the past is as equal as is as real as the future. The past part of me is just as tangible as the future part of me.
Yeah, they're intrinsically, they're just the same. They're made of electrons and protons and doing stuff. They're not categorically different at all. Maybe this will help. I'm not sure if this will help. People often say, gee, space-time is just four-dimensional and I'm just a worm. And their thought is like making a four-dimensional space, right? So you say, I've got a two-dimensional Euclidean plane. Now I add another dimension. I have a three-dimensional Euclidean space, right? I give a kind of a worm through that. Well, maybe I can add another spatial dimension. But that's not what's going on, because nobody thinks that space-time is a four-dimensional spatial object or has a four-dimensional spatial structure. This shows up technically. You use a Lorentzian metric, you get a light cone structure, you get a whole bunch of stuff that is not just adding another dimension. And that structure can be used to represent temporal structure as different from spatial structure, right? So the time part of space-time is different than the space part of space-time. It's just different mathematically, geometrically, structurally, in every way you can think of. So none of this suggests, right, that time disappears or something.
Well, I guess here's hopefully a clearer way of putting it. But to say that the future is real, looking at it in the same way that the past is, looking at it this way, is to say that not only is this fourth dimensional component of me already fixed and stretched into the past, so the past is real, but it is, in a sense, already fixed and stretched out into the forward direction, as opposed to growing into the forward direction.
The word already has a meaning in English, and it refers to stuff to the past. So no, your future is not to the past. So it is not already, if by already you mean what we mean in English by already. But that's trivial. Let's just say the future is to the future and the past is to the past. And, to say that the future is not, people do this all the time. They say, oh, you mean the future has already happened? No, the future is to my future. And already in English, the meaning of it is it refers to things to my past of the moment that I use it. It also has this indexical component, right?
I'm always talking about this, in my undergraduate classes where we talk about time, and then fatalism comes up and the block universe, and people will say, the future, if the future already exists and it's already fixed, then doesn't that mean there's no free will? And if you think of the kind of block universe, it's just a list of the actual things that happen. That's it. And it doesn't give you anything about the causal structure, about what could happen or would happen. It just tells you, so if I, hopefully I don't, if I die by getting, hit by a car, when the interview is over, that's something that would be true. Did that have to happen? Well, maybe if we threw in some physics and there was a bunch of causal forces and stuff to force me to, for that to happen, then maybe. But just the mere fact that it's true doesn't mean that it had to be true. So, in the fatalism, literature, they call it the modal fallacy, that people want to go from the fact that something's actual to that it had to happen.
Right, that's certainly wrong. And there's a good physical question about determinism, namely, does the state of the universe, suppose we throw in this foliation, it just makes things easier. So we can reasonably talk about the state of the universe right now. There are some issues about that in relativity, but let's leave those aside. So here's a good question. Given the laws of physics and the state of the universe right now, are there different alternative futures compatible with the laws of physics or not? If not, then you have a deterministic physics. You can ask that just as well about the past. You can ask, given the present state of the universe, are there alternative pasts that are consistent with that and the laws of physics? And it could come out either way. Determinism is a well-defined question, but it's not the one we're talking about. Whether determinism would take away free will or whatever, I disagree with that as well. I'm a compatibilist. I think there's no problem having free will, even in a deterministic universe, where in some sense, everything was already determined at the Big Bang. I don't think that takes away free will. That's another discussion. But anyway, determinism is just a very different question. Even if the world is indeterministic, I think there will be exactly one future, and the totality of reality will be specifying everything that happened to the past and to the future, right? Which will be four-dimensional in this mathematical sense of four-dimensional. Even if it's indeterministic, that'll include how all the indeterministic things came out.
I don't think there's anything really to talk too much more about on this. Well, there's a lot to talk about, but we don't have to. But just to try to underline one thing that Tim said, and so a good chunk of my book was about how the fourth dimension is not space. That the difference between the time-like directions and the space-like directions ends up has huge effects throughout physics, and then huge ramifications all the way up to critters like us, I think. And so, and I wonder how much of philosophy of time, or traditional philosophy of time, is actually sort of based on this idea that the block is this four-dimensional spatial block versus the block it is.
Well, just to put a bow on this then, if you're saying, Tim, that the future is real, only amounts to your saying that, using my example, that all of our space-time worms will grow and be concrete. And as I understand you, it does not amount to the assertion that it is fixed, which would be conflating the future with the past. Then we're on the same page.
Yeah, no, I don't. I don't think that's quite it, and I don't like the word "grow" there. Growing is something that persists through time can do. Right? A puppy can grow. Why? Because it persists through time, and at a later time, it can be bigger than at an earlier time. That's what growing is. Space-time worms, maybe you can say trivially they grow. I don't know. To say they grow seems strange, because when a puppy grows, it means at a later time, it's bigger than at an earlier time. there's this problem, as I say, it's the same problem, and let me just kind of ping this off you to see if this is what's in your head. People who say, okay, you believe in the block universe, and in a certain sense, I do. They say, oh, that's static. And I say, what do you mean it's static? I mean, the word static in English, or stationary, or frozen, or fixed, refers to things that persist through time and fail to change as they do so, right? In other words, being static only applies to things that persist through time. Just as changing only applies to things that persist through time. A single event can neither be static nor change because it doesn't persist through time. Now, does the block universe persist through time? Well, no, as I say, it's not in time. Time is in it, right? So it's neither correct to say it's changing, nor is it correct to say it is static. It contains all change, right? It also contains everything that happens to be static. But without putting the whole of space-time into yet a hypertime or something, you couldn't even ask a question like, is it static or changing? And we don't need a second order time. The only time we need is the one in the block. So I'm not sure if that helps or not, but I'm not, when you say things are fixed, I'm not sure. I mean, I just need an articulation of what the property is you have in mind and how you're applying it to the future. If you're saying, is the future fixed, you might mean, again, the deterministic question. Does the present state of the universe, together with the laws of nature, already determine what the future will be? I'm open-minded about that. I think it could go either way. I'm perfectly willing to imagine deterministic laws and indeterministic laws. But this just seems to be an orthogonal issue to everything we've been talking about.
You mentioned this issue of foliation earlier, which we haven't touched on yet, but I think it's going to come in here. And am I correct that relativity, in a sense, rules out presentism, at least, in the sense that because simultaneity is a human myth based on how we perceive our local environment, there's no such thing as the objective and current now throughout the universe? Maybe you could explain what foliation is. And
sure. So this is pretty easy. If you go back and read Newton, which is always a good idea, you can just read the first parts. You don't have to go through all the proofs and everything, but he's very clear. And Newton, actually, this is in a letter, I guess he wrote. He says a moment of time, I think an instant of duration, I'm not quite sure he uses one of those words, is the same in London and in Rome and throughout the universe, right? A moment of time. So what is he saying there? He's saying, I snapped my fingers, okay? That was an event. That's a local event in space and time, right? My fingers. The moment I snapped my fingers, something was going on in San Diego, right? Something was going on the moon. Something was going on Alpha Centauri. There's a kind of snapshot of the entire universe at that moment. That's a well-defined thing. And then there's another moment, and then another moment, and then another moment. The time just is a stack of these global moments or instants that proceed from past to future. Okay, that's Newton's picture. And that stack is what we call a foliation. So if each part of the stack is three-dimensional, because space is three-dimensional, and if I stack all these things up, now I get something that's four-dimensional, yeah? But it has this preferred slicing, right? You can take all the events that happened at the same moment and slice through there, and then a little later slice through there, and then a little later slice through there. That's a preferred foliation. That, it seems to me, is kind of required if I'm going to be a presentist, because one way of understanding presentism is to just take one of those gadgets and throw the rest away somehow and say all that really is one of them. But then you need that slicing. Now, in what happens in relativity, if we just take it at face value, is it just gets rid of that. It gives you a different space-time structure. It doesn't have that foliation. It just doesn't slice up space-time in that way. It gets rid of some of what Newton has, and it adds some stuff Newton didn't have. It adds a light cone structure, which Newton didn't have. It adds, so it's not just subtraction, right? It's replacement. There's some absolute structure in a relativistic space-time, including the light cone structure, but it's not this foliation. Now, maybe surprisingly, it turns out that you don't need the foliation to do Maxwellian electrodynamics. That's what Einstein realized. And you don't need the foliation to have a good theory of gravity. That's what the general theory of relativity pointed out, right? Worked out how to do that. It seems like you need it back again to do quantum theory. Okay. That's my own view. At least the easiest way to do quantum theory is to throw a foliation back in. But that's, as everything I say is a very controversial view. None of this is really part of our intuitive, I would say, part of our really intuitive picture of space-time, except insofar as our intuitive picture we know to be false. So let me, and then I'll let Greg go. Let me just say this last thing. So suppose I'm standing out at night and there's a supernova, right? So this bright light suddenly appears in the sky that I notice. And I kind of point and I say, look, a star just exploded right now. Now, everybody agrees. Newton agrees. Everybody agrees. No, it didn't, right? You're reacting to the light getting to your eye. And that star exploded millions of years ago, right? And we have this tendency to think that the things we are just now became aware of are things that are happening just now. But a little bit of thought, a tiny bit of thought, not relativity or anything else, says, no, that's not right, because what we're reacting to now is just what's hitting us now. And so the picture, the kind of naive picture that the world as it is now is the world as it looks to me now, we know that's got to be wrong. And once you realize that's wrong, then you see that this foliation is really playing that much of a role in your everyday thought about the world, right? It's just not. That's why you can kind of get used to relativity and live with it pretty easily. You can get rid of that absolute simultaneity and then say, well, I didn't really need it. I wasn't really using it for much of anything anyway. But you need it back for quantum theory.
Let me jump in. There's a couple of, there's two different directions we could go here. One would be the preferred foliation, if you need one for quantum mechanics. And then, just on the kind of common sense idea of a kind of objective present or objective simultaneity. I do think it's, as a kind of footnote to what Tim said, I do think it's interesting that although you could look way back that, historically, that there were always people saying that the speed of light was finite or many times, but the bulk of, I don't know how I would quantify this, or if this is really true, but the bulk of humanity for the bulk of time thought that the speed of light was infinite. And so they thought that what they were seeing, so when Tim was describing the supernova, I think most humans for most of world history thought that was happening, immediately. And so I think that's often a kind of revolution in our thought that we don't appreciate so much, that it's the kind of world we live in, that it is so intuitive that we, now we just think of the speed of, everyone thinks the speed of light is, traveling at a finite speed. And so, of course, all of these events they're all in the past. The really far ones are really in the past, and the close ones are just a bit in the past. But it is kind of a big revolution because if you really put yourself in yourself in the shoes of someone who thought that everything they saw was immediate. I mean, that is really quite a different world and world picture that you would get. And you could then, try to explain why humans would have that. And, the answer is that the speed of light is just so fast compared to our perceptual abilities and thinking abilities and nerves and everything. And, I think in the beautiful Garrosh book that I think I was first introduced to by Tim in a course. He says something like, if you wanted to get your two fingers to snap so that they're both space-like related to each other, so that there's not a possibility of light getting from one to the other, then I think in the rest frame, they have to be at the billionth of a second with respect to each other. And so it's almost everything is all time-like and in the past. So these things you're saying, well, that happened at the same time as that, perceptually, those are almost always, things that are time-like related to one another. And, but nonetheless, because we don't know this, we put together this kind of picture and think that it's grabbing something real.
Right. I mean, there's another way to put this, which is, it's just the same point again. Anybody who's been interested in relativity and opened a book has seen pictures of light cones, right? And it just looks like a regular old double cone. You have an event, and then it's past light cone, future light cone, right? And when you draw those pictures, you always adopt a convention where the speed of light is 1, which is why the edges go out at 45 degrees, okay? 45-degree cone. If you were to redraw it using everyday units, like, seconds and inches or meters or miles, what happens is that cone would flatten out. I mean, the bottom part would do this, become flat, and the top part would do that, with this tiny, tiny, tiny little invisible sliver between them, unless you went far, far, far away. And that looks very much like a leaf of a foliation, right? So this kind of Newtonian picture that there's just a single slice. Now, this has 2 lobes to it, right? As a part, no matter how flat it gets, there's still a little bit separating the 2 lobes. But intuitively, at everyday scale, you might as well be using a foliation, right? And then if you think light, then you could just say, oh, light is just instantaneous, right? Aristotle's theory of light sort of would make it instantaneous because it wasn't anything traveling from here to there. It was an actualization of a potentiality, blah, blah, blah. And that could happen kind of all at once. So yeah, you can sort of see the relativistic picture at everyday scales looks very much like Newton's picture.
Now, on the other topic, if you want to switch back, that's okay. But on the some listeners might have, if they're working philosophy or that, they might have had a small heart attack when they heard Tim say that quantum mechanics demands for the reintroduction of a foliation. But I don't think that's so bad. In fact, I was just in my graduate course. We did a little module on Einstein versus Lorentz. So even before we enter into quantum territory, and so I tried to play devil's advocate for about 3 hours for Lorentz, even before we go to quantum mechanics. So I do think relativity is the way to go. So I'll just officially state that. But if you think, so Lorentz was, so the main equations, transformation equations of special relativity are called the Lorentz equations, which tells you, of course, that Lorentz came up with them before Einstein. But but Lorentz thought there was a preferred foliation. And if you then think, well, why, and so this used to be a topic in philosophy of science for many decades, which was, why, that Popper and Lakatos and Elie Zahar would argue about why switch to the Einsteinian picture. And so I put myself in the shoes of Lorentz. Was it rationally demanded that Lorentz switch, say in 1908 or 1910 or something, so like before general relativity, and think that there is no preferred foliation? And people will say, well, look, in the Einsteinian picture, it explains all these miracles and conspiracies that happen in the Lorentzian picture. But are those things, so if you try, so on a Lorentzian picture, if you move, some kind of object that's conducting, and then you try to, it will predict that there's different phenomena in the rest frame versus the moving frame. But then if you try to measure the difference, then it sabotages that measurement, and it ends up saying that the observations will be the same. And so people say, well, it's conspiratorial and the Einstein picture is better. But it's not conspiratorial in the sense of a bunch of, banana peels that have to be, stepped on by the experimenters, and that there's just special initial conditions that require this. On the Lorentzian view, Lorenz would just say, look, the laws just predict this. Those laws also happen to be the best laws that physics has ever invented. And I'm just following through the consequences of my laws. And this whippersnapper Einstein comes along and puts it all in a different way without the foliation. Well, okay, but you could then consider moving to that. But to think that the Lorentzian thing was conspiratorial or that just seems to me wrong. So I was trying to warm the students up to seeing that it wasn't so obvious a slam dunk, why you would switch from the one to the other. And then I think that this discussion is also then relevant to when you then turn to quantum mechanics, where quantum mechanics you then have, this kind of, non-locality that's, also that it gets written. Well, trying to explain the non-locality ends up invoking often mechanisms that pick out a frame.
Let me just add one just historical note for people who get interested in this. The way both Craig and I have been presenting relativity, both special and general, that wasn't even quite the way Einstein was thinking about it in 1905. I mean, it was Minkowski who got hold of Einstein's work and then realized he could interpret it in this kind of geometrical way. And there was some resistance of Einstein himself to interpreting that way for a while. I mean, I think eventually he accepted it. So understanding the exact terms between Einstein of 1905 and Lorentz is even more complicated. Because the way we've put it is more in this geometrical language that really was only developed a bit later for thinking about the theory.
And does the foliation picture, am I right then in thinking that it will enter quantum mechanics again because of non-locality, and that we want there to be this absolute simultaneity relation between two entangled particles?
It's not the entanglement. It's that what Bell's theorem shows, and this is really in some sense independent of quantum mechanics because it's just stuff in the lab. Bell proves a theorem that covers all causally local theories. Okay, all of them. Quantum, any theory. It doesn't matter how it's built. If essentially all the causes of an event lie in or on its past light cone, which is essentially the definition of causally local, then Bell shows that there are certain correlations that cannot be predicted or explained by a theory for events done in separate labs far away from each other and at about the same time. Technically, it's space-length separation. That's the theorem, right? So the theorem says, if you have a causally local theory, it cannot predict such and such. Yeah. Quantum mechanics predicts the thing that can't be predicted. But then more importantly, essentially, you go into the lab and check, and Bell's inequality is violated. So then we say, all right, that says the world contains some causal non-locality. And now the question is, how do I implement that in a clear, precise way into my physics? The easiest way to do it, I'm not saying the only possible way to do it, but by far the easiest way to do it is to add a foliation, to appeal to a foliation in implementing that non-locality. You can really tie yourself in knots or try lots of tricks to do something else, but it makes your life 1,000,000% easier in trying to just write down a clear theory that can make these predictions, to have a foliation to play with. And then you can say, look, it's no longer that all the causes have to lie in or on the past light cone of a theory of an event, but all the causes lie to the past of it, right? You can still have that, as it were, causes always precede their effects. All the causes of an event lie to the past, where I've got this foliation. So I've sliced the space-time. I've got this event. I have this slice through it. Then everything to the past, that's potentially could have an influence on it, right? Then you can write down the theory. Then you have no problems. Now, people got so used to not liking the foliation because of relativity that they recoil from it, right? They have this gag reflex. If you say, I'm going to introduce a foliation. To me, this makes no logical sense, because special relativity was developed thinking of Maxwellian electrodynamics. That's a causally local theory. General relativity was developed to have a theory that could replicate Newtonian gravity, which, as it was implemented, is a causally local theory. Neither of those theories could violate Bell's inequality. So, of course, neither of those theories needed this foliation. They didn't need to account for the phenomena that we get out of, quantum mechanics, this violation of Bell's inequality. Once you have that kind of phenomenon, you might say, well, gee, I need to do something, right? I mean, something's happening that is not easy to account for. Why would it be easy? I mean, Einstein was smart, but he wasn't that smart, right? I mean, he couldn't have said, oh, I understand that in 30 years, or in 70 years, somebody's going to do an experiment that's going to violate this inequality that I don't know anything about. And in order to accommodate that, I better put a foliation back in, right? So, he reacted quite reasonably to the problems he had before him, but they just didn't include violations of Bell's inequality.
Well, maybe I would just add on the foliation just that, it's, I think, an active, an interesting, open question about whether other theories also require foliation. So whether quantum gravity ends up needing one, or even general relativity. So the theory simplifies an awful lot if you do pick up foliation, and you can explain things so nice. A bunch of issues would go away in general relativity if you did have a foliation. So, for instance, like energy is not conserved in general relativity, which then makes explaining gravitational waves and that kind of odd. If you picked a foliation, a lot of those issues would go away. So it might turn out to be useful. So I'd hate for it. I mean, I don't get to pick what kind of reality I live in, but it'd be unfortunate if the only sign of a preferred foliation was the Bell non-locality. If a foliation could be put to work in some other way, that would be really, it'd be extra reason to posit it, I guess.
I adding on to all of the extremely controversial and people will react to strange things I said today, I'll just add one here, which we can come back to later if you want. I actually think it's very likely we can superluminally signal, and that if we can do that, we can actually see the foliation. We can identify it empirically. That'll sort of settle the issue. Yeah.
I didn't know this about you, Tim.
Recent work by Siddhant Das on arrival times. I mean, we could talk about arrival time experiments. There's a very quick argument that if Siddhant was right about this stuff and you can see it, then you could actually rig up a superluminal signaling mechanism.
Could you start, though, by saying what superluminally signaling means?
Sure, that's easy. I mean, if I want to send you a signal nowadays, I've got to send you an electromagnetic wave like light or something like that. And of course, that's not superluminal. That goes at the speed of light. So, signaling involves a sender who does something. and a receiver who receives something from which they can make an inference that at least increases their chance of being right about what the sender did, right? In other words, there's information. The receiver sees something that provides information in Shannon's sense about what the sender did. That's what signaling is. Signaling like light signals means you can't do it faster than light. The signal can't get there faster than light can get there, right? If you can do something superluminally, if you can signal superluminally, this is something many people think cannot be done. Then you could really just settle in the lab if there's this preferred foliation of what it is. You could do experiments and actually identify it empirically. I'm not sure. You look still puzzled, but I'm glad. I mean, Craig or I can. There's nothing very complicated.
So Robinson, I think most people don't think you can do superluminal signaling because in ordinary quantum mechanics, you get your system is described by a state. It's evolving with time, and then you get your predictions from something called Born's rule, which gives you a probability distribution of where stuff should be. And then, in ordinary quantum mechanics, you can prove that if you're restricted to that, then you're not going to be able to superluminally signal. And so you could be, far away. I could be on I'm on one end of the universe. You're at the other, and we're measuring a kind of Bell pair. There's no way I can, use that in any way to signal to you.
Right, and let me just add here as motivation. I mean, again, what Bell proved is that just to get the observed statistics, you need some causal non-locality. So I'm doing an experiment. Craig is far away doing his experiment. Okay, if we just the data that comes out of our two labs could violate Bell's inequality, which means what? It means either something I did affected Craig's result or something Craig did affected my results. Okay? Now you might think, well, gee, if that's true, why can't you just signal each other? Why can't Craig arrange, to do this or that, and then I can look at my result and figure out whether he did it? Well, it turns out that it doesn't automatically follow, even if there's non-local causation, that you can use it for signaling. To signal, you need some additional conditions.
Yeah, and so it's really, so I'm just getting, if we think of, spin up or down, I'm getting like a random distribution of sort of heads and tails. Tim is there in Lugano getting a random distribution of heads and tails. Just looking at the heads and tails, there's no, I can't tell, what is Tim telling me? I don't know. I just got this random, I can't control whether he gets a tail or a head. He can't control whether I get a tail or a head. It's random. There's no way to tell. Except maybe, well, then I'm wondering what the arrival time.
Right. So this is, I'm sorry, Robinson, but you should slow us down. But
no, you're fine. You're fine.
I'm looking this to Craig right now because it's new stuff. So Craig says quite correctly, there's a theorem actually proven also by John Bell and sometimes called the Nobel telephone theorem that says under certain constraints, this non-locality cannot be used to send signals, right? Which ought to surprise you because you're saying there is a causal connection there, but you can't use it to signal. Those constraints are that, among them, that everything that Craig can observe in his lab is represented by a certain kind of operator called a Hermitian operator, right? So just a piece of mathematics. And it's using that you derive the probabilistic predictions. And that everything I can do in my lab is represented by a change in a local Hamiltonian. It doesn't matter. But there are, restrictions on what I can do and what he can see, right? It turns out, for kind of well-known reasons, there's some stuff you can see that is not associated with any Hermitian operator. And one of those things is arrival times, right? So if particles are getting to Craig, one of the things he can do is we arrange that the particles will be sent from some source at some moment, and he can time when they arrive in his lab. Okay, so that gives him an arrival time. If I send 1 million of particles, there'll be a whole arrival time distribution. They won't all get there at the same time. It'll be a distribution. There is no Hermitian operator that corresponds to that. That's an observation he can make, and everybody agrees. There is no Hermitian operator that you can use in the standard quantum formalism to predict what that will be. And what Siddhant Das has been looking at is how all this plays out in Bohmian mechanics. And it just turns out that there are spin dependencies of these arrival time distributions, which, unless you do something about it, if you can see if you can see these differences, then you can promote that into a signaling mechanism. And it evades the theorem because you're just not using Hermitian operators. Anyway, this is all very controversial.
Yeah, it's super interesting. I mean, maybe you could say, but maybe you can't because maybe it gets too technical. But so the Copenhagenists, the standard interpretation, I thought would always just say, well, okay, I can't, I don't have a Hermitian operator for arrival time, but I still have, I can still have a collapse of a bunch of positions that are going to correspond to the, when you measured the. Because Copenhagen is so mushy, that gives them a kind of flexibility.
Yeah, look, think about what you said. When I measure, I mean, if I just have a screen and when a particle gets there, it's going to set off, a flash, and I've got a really good, picosecond clock that's going to time these things. It's just, even technically, it's not clear what quantity you could calculate using the standard tools that would give you a probability distribution for this. And everybody knows, it's like everybody knows there's no time operator in quantum mechanics. I mean, this is a kind of piece of lore. Anyway, nobody's going to disagree about that. And so it might not surprise you that issues of arrival times, they're not so straightforward.
I'm generally curious about measuring time versus measuring space. I mean, it's pretty clear, at least on an intuitive level, just what it is that I'm measuring when I measure like this I guess the top of my laptop. But what is it that we're measuring when we're measuring time or watching a clock?
So let me just give you a surprising answer. Let's leave quantum mechanics aside now. Let's go back to relativity, okay? Oddly enough, in relativity, the length of the size of your laptop, that's really problematic. That's the hard part, right? What clocks measure according to relativity is you have this picture of, as you say, a space-time worm, right? That as it were you and the clock and any other kind of everyday item is this thing that kind of wiggles through space-time. And it always wiggles in a way that it doesn't go faster than light. So as we say, it threads the light cones. It's always kind of going up like this. And that path that the thing goes through has a length in relativity, a perfectly determinate, precise length, independent of reference frames, independent of any conventions, whatever, that's measured in a quantity called proper time. And what a clock, this is essentially the definition of an ideal clock in relativity. It's like a good odometer, right? What does a good odometer do? It accurately marks off distance that the car has traveled in space. A good clock is clicking off distance that it has traveled along its world line as measured in proper time. That's the relativistic answer.
And then I think this distance, though, immediately brings in the direction of time. And we have, intuitive, good prima facie evidence for there being a direction to time. And that, we remember the past and we don't remember the future. The immediate future tends to become the immediate past, and so on. But is there...
pretty reliable tendency there, isn't
Yeah,
it?
quite reliable. It doesn't seem to go the other way. But is there a more precise way of describing what this means along the lines of the description you just gave for measuring time?
Well, you could look at different features that are associated with it. So, sometimes people talk about a causal asymmetry or an epistemic asymmetry, and then specifying carefully what those asymmetries are is a thing you can do. So, like the epistemic asymmetry is often glossed as, I know more about the past than the future, but that's not really all that precise, because it's not like anyone goes around counting the number of propositions that we know about the past versus the future. And so I think David Albert, nicely puts it where, it's more about the character of about the way we know about the past and the future. Because we can know about the future. I can take the present state of the universe, calculate out, when Halley's Comet will come next. And you could say, that I know that Halley's Comet is going to come, whatever date that is going to come. But, what I'm doing is I'm doing a lot of calculation, and I'm taking initial conditions and I'm evolving them forward with the laws. And it seems like I can just know stuff about the past in a different way. So you might characterize that asymmetry that way. So you have all these different types of asymmetries, and that's, so when we talk about the direction of time, it's really like a whole mess of different asymmetries.
Yeah, I mean, I would say among them, and again, everything I'm saying here, I always preface this is very controversial. A lot of people will, throw tomatoes at their screen when I say this. I would say, the fundamental one is causes precede their effects, right? So that's a heck of an asymmetry. That underlies a lot. And it underlies also explanatory asymmetries of everyday life. For example, you'd say, look, someone asks, well, why is the Earth right where it is right now in the solar system? And if someone were to say, well, 10 months ago it was here, and then we've got the laws of gravity, and there were these forces on it, and it, then 10 months later it ends up here. Most people would say that's at least, that's a pretty decent explanation. I mean, you might worry about the thing going in. Nobody would think it was a good explanation to say, well, 10 months from now, it will be in such and such a place. And if I work backwards, which I can do, I'll find that given that 10 months from now, it'll be in such and such a place, it must be here now. Nobody would think that's an explanation, right? And nobody would say it's causation either. They wouldn't say the future state is causing its present location, but you would say the past location is part of the causes of the present location. And I don't think this is just a tendency, unlike, the reason why I want to bring this up is unlike epistemic axis, where you might kind of be weighing how much can I accurately tell you about the past versus how much can I accurately tell you about the future. And it's, it's a very uneven thing, but it's still, I think in the case of causation, it's just causes precede their effects, period, end of story, right? And so all of our other concepts that rely on causation inherit an asymmetry insofar as they make any reference to causation at all.
Yeah, so I think this is a place where Tim and I just differ, where I'm thinking that the physical asymmetries are what explain the causal asymmetry, that there's not maybe I should put it, the uncontroversial physical asymmetries are what ground the causal asymmetry. And that the causal asymmetry isn't sort of fundamental in some way. And I think, I have the intuitions that I do because I live in a universe such that there is this predominant direction of time given by by the processes in time. And that gives rise to me thinking of causation as this kind of really fundamentally directed thing, but really, if the kind of arrows, if you drew the arrows so that there was backward causation, that would be okay with me if the universe turned out to have systems like that.
So again, I seem to be making incorrect interpretations a lot of the time of what you two are saying, but that's good because then it just leads to clarification. But from what it's sounding like to me is that, Tim, for you, the direction of time is something maybe primitive about the way the universe is, and it depends on, it's just a product of causation. Whereas for you, Craig...
Other way around. Causation is defined, a part of the definition of causation is that causes precede their effects. So it's not that the direction of time is causation, but that causation, right, in the definitory, by the way I understand it, the idea of backwards causation is, as it were, just impossible immediately.
By definition of what causation is.
Yeah, by definition of causation. You don't need causation to define that time as a direction. And you're right. My view is that directionality is a primitive and further inexplicable feature of it. It is the feature in terms of which one would go about explaining a lot of these other arrows or temporal asymmetries that Craig's talking about, right? So, look, there's clear temporal asymmetries. I mean, typically, if you had pictures of somebody with gray hair and a picture without them with gray hair, you could put them in correct temporal order, right? So there's an asymmetry in over a human life between the gray-haired periods and the non-gray-haired periods. But of course, that's not at all exceptionless, because dye your hair, right? Or maybe you take a pill that suddenly restores the color of your hair. I mean, there's nothing. This is just now a matter of statistics. And I think ultimately, of course, that's an actual asymmetry. It needs to be explained. And I think there will be causal explanations, but those causal explanations will already appeal to the directionality of time in identifying what's a cause and what's an effect. So that's the way I go about this. And sitting at the bottom, there is fundamental.
Yeah, so my position is that flipped, so I'm trying to then explain this causal arrow from a bunch of other arrows I get in physics and the other sciences. And so that's a kind of divide. So I think, I don't really have a horse in this race exactly, but in my gut, I think, I've already got a lot of arrows, and let me see what I can do with them. And so if we could explain using a bunch of different arrows that are in physics, the causal arrow and the knowledge arrow and all of that, then that would be fantastic. So I don't want to jump to just that it's primitive. So for me, that's always a kind of position of last resort. And so I don't know that it's not primitive. So I don't know that Tim's view is false. To me, it's open question, but I would rather at least try to come up with a theory with a bunch of existing arrows to explain the other arrows. I don't know if that was clear at all.
No, that's totally clear. It sounds kind of like the parallel postulate in mathematics. I mean, people want to get away with the fewest amount of primitives and axioms that they need. And it's something similar here. You would like time to be determined by the laws of physics in the way that something like, I don't know, maybe gravity is, as opposed to taking it as primitive itself.
Yeah, that's right. So try to do more with less.
And is this sort of disagreement between you two, how would it be adjudicated? Is it something that experiment could confirm or disconfirm, way one or the other? Or how do you get past this sort of, I don't know, maybe this is intractable and it's just going to be a matter of taste?
This is really like a more joke but we take a time reverse person and ask them if they're conscious, and then that would adjudicate the question between Tim and I.
Yeah. Yeah, I don't think experiment is, unless, look, my view, because of what I just said, has the consequence, unless you do something really screwy, that there can't be causal loops, there can't be backward causation, stuff like that, right? Because causes always precede their effects, and in a normal space-time, that you never go around, right? Now, if one could imagine, if there were such a thing as backward causation or circular causation or something like that, that would put very strong constraints or allow really otherwise weird things to happen, or demand maybe that otherwise extremely strange and what would seem to be inexplicable things happen. And so if somebody said, yeah, I have a theory of time, and furthermore, I'm going to allow backward causation, or I'm going to allow these loops, and furthermore, I think we can set up in a lab a situation that will have these things. My guess is, at least for many of these, they would predict things that I wouldn't be able to predict. I really wouldn't be able to explain them, because, that would put these monstrous constraints on things that I don't have. So that could certainly be indirect evidence, right, of the normal kind. We say, gee, theory A, here's an actual phenomenon in the lab. Theory A handles it easily. Theory B doesn't handle it easily or at all. That's some reason to believe theory A. But I don't know of anything on offer of that sort.
Yeah, for me, it's definitely not thinking about closed time-like curves and time travel or any of that. It's more the sort of explanatory challenge. So, can I get the knowledge asymmetry from the thermodynamic arrow? That is not easy. So that you have a well-defined thermodynamic arrow, everyone agrees that this exists and is a thing. But as I think it was Jos Hufvik said, if you put a person in a refrigerator, they don't start remembering the future. And so, it's very, so it's not so easy to get so if you want to go from the thermodynamic arrow to the knowledge asymmetry part of the direction of time, it's not so easy. David Albert has a massive program trying to do this. Before that, Reichenbach. But anyway, it's not easy. You could then try to do something similar also for the causal arrow, counterfactual arrow, explanatory arrow. It's not easy, but part of it not being easy makes it a kind of fun challenge. And if you were successful, then that would be, I think, quite an achievement.
Yeah, and I should say, look, the first thing that Craig talked about, we talk about temporal arrows just meaning that there are at least statistically temporal asymmetries, right? Statistically, many more people have their gray-haired period of life later than their non-gray-haired period of life, right? That's just a fact. You could have a baby born with gray hair that later, it might not be universal, but it's certainly a manifest statistical asymmetry. And there are these asymmetries of knowledge and these other asymmetries. There are thermodynamic asymmetries and entropic asymmetries and so on. On my view as well, it's not like having a primitive direction of time just magically explains all these. It doesn't. And there's a question of whether some of them are deeply connected to others of them. And it would be interesting to find out. Certainly, it would be interesting for someone to give an argument. Just take the one I gave. Is there any connection between having gray hair generally in the later years of life and entropy? I kind of doubt it, because I don't think that there's gray hair is more entropic than non-gray hair. I kind of doubt there's a connection there. I think it's probably more an accident in genes and various things. But sure, there are lots of these asymmetries, and to the extent that you can explain one or anyway, connect one to another, you're getting understanding, and it's a worthwhile project. And you should certainly push it to see how far you can do it. But that taking my position about there being a fundamental direction of time doesn't foreclose that at all.
No, but I would like to see more, maybe I just want a more nuts and bolts picture. Well, I'll tell a little story, which I maybe I've said to Tim before, or maybe not. Anyway, you'll find it amusing, I think. So where I went to graduate school was with Tim, and so I was taught by Tim, but also mutual friend and colleague, Bob Weingart. And so he had a theory a little bit like this, where he said, well, in general relativity, people often talk about time-orientable space-times. He says, well, let's just actually orient it and put in a kind of vector field all over the space-time pointing to the future. And so what this means sort of intuitively is, well, space-time is orientable, if temporally orientable, if you could sort of consistently color, say, the future lake cone, like red. I've got a diagram, I just consistently color it red everywhere. But now let's have an actual field on there that points to the future everywhere. And then the thought was, a charge, which way would it radiate? It would consult the vector field. And so a charge could be advanced or retarded. It would consult that and then decide, well, I'll be a retarded radiation. And I said to Bob, yeah, but what is this consulting? How does it actually happen? He said, well, he saw a paper in a Japanese physics journal, which gave a kind of mechanism for how this would happen. But he said he couldn't find the paper again. And my thought was, well, until you find that paper, I'm not really going to see how this vector field does any work.
But I'm going to turn on the light because they sharp here. Let me actually make a comment. I mean, I don't remember ever hearing that story. It's an interesting story, but it actually does, I think, indicate what I had in mind, and I think Craig would agree. So one of the asymmetries people talk about is this radiative asymmetry. So they say, look, build a big radio tower, and you can drive electrons up and down it, and then you get these radio waves that radiate out kind of spherically from the tower. Yes? That happens all the time. Easy to do. People do it all the time, and they send out radio signals that way. Send music. The physics allows, as a possible physical solution, the time reverse, in the sense of, instead of radio waves going out from the tower, they could be collapsing into the tower. And when they get there, they would then drive a big current up and down the tower. But we never see that, right? That's true, right? We see the one all the time. We don't see the other ever. And people have said, well, why is that? Because they're both allowed by the laws of physics. Now, there's something a little funny about thinking you have to explain why something allowed by the laws of physics doesn't happen. I mean, it's allowed by the laws of physics that I win the lottery, but it never happens. I mean, does that need an explanation? Anyway, but some people have said, I think quite correctly, this can be assimilated to entropic issues, that somehow to send in a coherent collapsing wave, you'd need the emitters of that, which would be all around, way out here, very carefully tuned and organized to send the wave out from all these different locations at exactly the right time and exactly the right amount so that it collapses into the tower. But sending the wave out doesn't require that. You just turn on the thing at the center, right? It does this, does that. So there seem to be connections between entropy, various entropic or thermodynamic asymmetries, and the radiative asymmetry. And I think you make progress by seeing those connections and saying, yeah, it looks like this asymmetry at base, if it's not literally the other one, it's kind of on the same basis as the other one. I think that's really good work. But notice the way the way I even stated the problem presumes there's a direction of time, because I said, look, all the time you see this and you never see that, but the only difference between this and that is the direction of time, right? It's in the one case, the earlier time is with all the radio waves right by the tower, and the later time is them far away. And in the other one, the earlier time is all the radio waves far away, and the later time is them all collapsing into the tower, or the difference between going in and coming out. That is the direction of time. So I kind of presume the direction of time to even state the puzzle, which suggests that it shouldn't be taken as bringing the direction of time itself into question. But there is an asymmetry there. There sure is. And we ought to try and understand it.
Mm-hmm. I think we could probably talk a lot more about the direction of time, but in the interest of time, there are a couple more things that I wanted to talk about before we finish. I want to talk about time travel next. And before we get to the specifics, I have a broader question. And just what is the purpose or utility of theorizing about time travel as a philosopher? Is your goal to carve out a direction for actual engineers to begin working, or is it just fun, or are the thought experiments meant to tease out possible problems with how we conceive of time, or a mixture of this and other factors? Because it seems like it might just be like science fiction fun, basically.
Well, I think if I can start, I think if we just think about it as a topic in philosophy and in philosophy courses, so there's a kind of independent history in physics, I think, about why people talk about time, closed time-like curves and time travel. But, in just in philosophy, it is a great topic to sort of tease out many different sort of thoughts. The philosopher David Lewis used to teach a whole semester-long course on time travel, because it would implicate all these issues with time, direction of time, free will, fatalism that we discussed earlier, personal identity. So it's a kind of great, it's a kind of wedge that you can tease out different sorts of views, different sorts of issues, and a whole range of different views, topics. So I think it is good as a thought experiment. And then, in philosophy, I think most philosophers thought for conceptual reasons, time travel was impossible until there were papers by Paul Horwich and David Lewis in the early 70s that then I think convinced people that time travel was at least conceptually conceivable, not incoherent. And then, of course, coupled with relativity, general relativity allowing, or at least has solutions that accept or have time travel in them, then philosophers, really started to warm up to time travel. Does that seem right, Tim?
Yeah, I think everything you said is correct. Of course, the original target, which is, time travel is logically inconsistent. That was way too strong.
Especially that people are making those arguments when already there were things like the Gödel solution in general relativity, which, if it was mathematically consistent and physically consistent.
Yeah, exactly. And then
it had to be conceivable.
Clever science fiction writers writing all these clearly, logically coherent time travel stories. But that was way too strong. What we should ultimately care about is it metaphysically possible, right? Is it consistent with the very nature of time itself that this happened? That will come out differently depending on the account you give of the very time itself, right? On my account, it isn't, right? On some other people are trying to give accounts of time in which it is. So at least it's a good test case to see how these accounts come apart, right? To see what they're committed to and what they're not committed to. It's certainly, none of us are designing time machines, right? None of us are trying to help engineers actually create time travel.
That'd be a
But
good side gig, consulting.
Yeah.
Now, Tim, I wonder what you think about, so I've been thinking, so Robinson, so general relativity allows some models of some solutions to Einstein's field equations. So if you think of these as of the possible worlds of the theory, it then allows for some where you have time travel. So famously, Kurt Gödel's solution, but there are many others which would allow for time travel. But then, I wonder whether, when we think about general relativity, what would be lost? So I'm thinking about this from a kind of Humean laws of nature sort of thing that I'm sympathetic to. If we just cut those out, so we just restricted our general relativity to, this would be a technical thing, but just restrict it to, say, the globally hyperbolic solutions. So these are ones, there's a step below globally hyperbolic where you get all of them have closed time, all of them have cosmic times and no closed time-like curves. But basically, these would be like the nice, well-behaved space-times. And what is really lost if we just cut out all those kind of bad boy space-times that have time travel, since we don't actually see it? So I wonder whether this is a kind of picture where that kind of Humean stuff ends up aligning with your sort of fundamental direction of time picture, because I just don't see a need for these.
Well, yeah. And I think it's worthwhile pointing out, and again, Robinson, you should slow me down if what I'm about to say goes too quickly. But there's some things we've already mentioned. So a space-time is temporally orientable, as Craig said, if basically you can take all the light cones and divide them into two classes, the future ones and the past ones. And that as you move continuously through, the future ones just go into future ones, right? And so an example where you couldn't do this is sort of like a Mobius strip thing, where you would take this space-time and give it a half twist and glue it back together, so that if you, as it were, start here and future is this way, you go around and then that arrow is now pointing down. So that's not temporally orientable. Now, there are solutions to Einstein's field equation that are not temporally orientable. But physicists never take them seriously as representations of the way time could actually be. They just reject them, saying, look, that's not a realistic solution because it's not temporally orientable. I think that's perfectly reasonable. What they also tended to do was say the same thing about closed time-like curves or time travel. Yeah, there are solutions, and there are fancy solutions like Gödel's, and there are simpler solutions where you just roll the thing up. And many physicists just ruled them out and say those are unphysical solutions, right? They're mathematically well-defined, but they don't correspond to the way the physical world could be. Why? Because time doesn't go around in a circle. That's why. I think that's a perfectly reasonable thing to do. I mean, a lot of this is pushed by people who are so enamored of the mathematics that they think, oh, I've got all these solutions to the equations, I have to treat them all seriously. But you don't, and physicists never have. You would like a sharp criterion for separating the sheep from the goats, as it were. But in this case, we have a sharp criterion. So I agree with Craig. I don't think you would lose anything. You'd certainly lose none of the explanatory power of actual physics, because we don't have a single physical phenomenon that seems to require anything like time travel. So it's not like we need it, right?
Philosophers would lose a lot of fun, because a lot of these times are really fun, and part of me would die if we got rid of them all. But yeah, intellectually, it's very hard to defend them, I think. I mean, sometimes people say, well, maybe we might use them, or they'll point to some speculative theory that maybe might require them. And then, but then I think the thing to do is just to say, well, come back to me when that theory is really a good one and actually does require one.
Well, just a quick comment. Craig, you mentioned Paul Horwich a few minutes ago. He's definitely one of my favorite people in philosophy, Tim's colleague. We had a conversation on the podcast about realism, which is kind of funny because he doesn't like the term realism, and then he came to Stanford, and that was great. But I knew that he got his start in the philosophy of physics, but I didn't know he'd written about time travel. So that's good for me to know.
Also, he has. I wonder if I have it here in my office. I think it is the most beat up book I have is I was doing my dissertation on the direction of time, and he had he had a book Asymmetries in Time, and I don't even think the book has a cover anymore. But it was so read and reread back in the early 90s. It's a really wonderful book.
Well, what I was going to ask next, though, after that quick comment, was whether there is any compelling logical or metaphysical argumentation against the possibility of time travel that should preclude or even going farther into the physics and philosophy of it. But Tim, I mean, I had on the logical side something like the grandfather paradox in mind, but Tim, you mentioned that suggesting it's logically impossible is too strong, but that it is metaphysically incompatible with your view of time. So I guess I have two questions. Since the grandfather paradox is such a common topic and it hasn't come to the podcast yet, maybe we could talk a bit about it and why you think it's too strong or doesn't rule out time travel. And then on the other hand, I'm curious about why it's incompatible with your view of time.
Okay, so the incompatibility is pretty simple to state. I think that, as I say, by definition, causes precede their effects. And I think this earlier-later relation is transitive. So if A precedes B and B precedes C, then A precedes C. And I think that nothing that nothing precedes itself, right? So then there can't be loops, right? It means you have what we call an acyclic graph. If we put in the arrow from every earlier event to every later event to it, that you'll get a graph, and it's got to be acyclic. And that rules out that kind of time travel with backward causation or circles of causation. Now, traditionally, philosophers from forever thought that things can't cause themselves, right? That there's something a little screwy about saying that something caused itself, because you say, but wait, if it wasn't there already, how could it cause itself to come into existence without already being there? And if it's already there, then nothing needs to cause it to come into existence because it's already there. Things like that. I mean, those are, tricky little arguments. I don't think you can get literally a contradiction out of just the words or the words plus the temporal structure. I can get a contradiction because I have a particular theory about the temporal structure, that it has it has transitivity in it's nothing ever causes itself or nothing ever precedes itself. Then you can run consequences out of that. But people who disagree are just going to deny those assumptions, right? They're going to say, well, gee, I don't think it has to be transitive, or I think it's okay for something to cause itself. So these are not literally deriving P and not P, which would really be a logical problem, right? You know that it's logic. You know that doesn't happen because, as I say, there are just lots of nice, coherently written time travel stories in the science fiction literature, like All You Zombies, or in the movie 12 Monkeys or whatever. There are many more crummy ones that are inconsistent and don't make any sense, where you go back and change the past, as they say, like in Back to the Future. That just doesn't make any sense because the past only happened once. You might be able to influence the past, but one thing you can't do is change it. But there are consistent ones, and the existence of consistent time travel stories shows you're not going to get into trouble with logic. The normal idea, as you know, is someone says, well, if I could travel to the past, then I could travel to the past and kill my grandfather. But if I killed my grandfather, then I would never have been born, and then I couldn't travel to the past. And so that's a contradiction. There's a bunch of literature in the literature of mathematical physics about if you take a scenario like that and actually try to realize it using actual physics written down as equations, and if the equations have certain mathematical properties of continuity and so on, you can actually prove theorems, fixed point theorems, that show there will always be a solution. You'll never get into a case where you set up a situation that doesn't have a solution. It'll always have a solution. Sometimes it'll have more than one. I go into the past and try and shoot, well, let me just do the auto-suicide one. It's easier. I go into the past to try and kill myself because I'm so miserable and I don't want to go through this, right? So, let me go back, a little earlier and kill myself. So I go back, I grab a gun, I go back, I shoot at my earlier self, but my arm vibrates, right? My aim isn't true. And I just nick my spine. And I nick my spine in exactly the spot that causes my arm to no longer be a reliable aiming mechanism. So that when I try and kill myself, the very thing. Now, the existence of such solutions, which don't violate the laws of physics anywhere, is proven by various fixed point theorems under certain statable conditions. And again, if you have a mathematical solution that's okay, it's illogically okay too. So often the grandfather paradox just makes assumptions which, if you try and make them into clean physical assertions, turn out not to be things you can really defend. So I don't think that's the right way to get rid of the problem.
I interviewed...
That went real quick, I know. I'm sorry.
No problem. I interviewed Avi Loeb, an astrophysicist at Harvard, and I don't know if this came up in the podcast or just when I was preparing, but he said, or I read, that he only likes science fiction movies that are compatible with physics as he knows it. And am I correct in hearing you, Tim, though, that you, even though you don't think that time travel is compatible with your views of physics and time in particular, you can still enjoy time travel movies like All You Zombies?
I enjoy a well-made, consistent... I don't like the ones that are logically inconsistent, right? Like Back to the Future. That annoys me. I like it when they put the effort to make them logically consistent. And I like if they kind of gesture at some physics that might be relevant in a coherent way. I appreciate the effort.
Yeah, 12 Monkeys is fantastic, I've always thought. And yeah, I have my students often write assignments on analyzing whether some time travel story in fiction is consistent or not. And I always tell them that they can't use Back to the Future, any of the movies, because it's just so ridiculously stupid that it's just they can't do it. But it is kind of interesting. Yeah, what I especially like about 12 Monkeys is that it's, a lot of the time travel stories that are consistent, if the protagonist had read a lot of philosophy of time travel, they would not behave the way they did. But 12 Monkeys is one of the exceptions to that, because they accept up front that they can't change the past, but they can still learn from it and influence it, and that which is really awesome about that movie.
And Craig, returning, we can always come back to movies, but time travel is compatible with the way that you view time, or it isn't?
Circling back, I think a kind of quick little checklist would be, I think Tim and I agree that time travel is logically possible. We probably disagree whether it's metaphysically possible. And then we are both heterodox in thinking that maybe the arguments for it being physically possible are not as strong as commonly taken in the field. So I have no problem with metaphysically. I have no problem at all with it being metaphysically possible. But I think because it doesn't happen, and I read my physical possibility as best describing what's actually happening, that maybe then in that sense it physically couldn't happen.
And I know
but conceivably, no problem.
I know that.
There is, I'll just mention for people who understand this comment, Craig said this before, his Humeanism about laws is coming into what he just said. And since I'm not a Humean about laws, this is where one of our disagreements would lie. But we don't need to go into that. But that's for people keeping score at home. That just happened.
So I would claim that not only am I Humean about laws, but I'm the most Humean about laws.
Well, I started off by asking whether or not you guys consulted with people trying to engineer time machines, though I didn't put it that way. But I wonder, as somebody who does think that time travel is at least conceivable, do you at all think about how it might be done, or if it's actually technologically conceivable? I'm thinking, I don't know what movie it is. One of you probably knows, or maybe it's in multiple movies where somebody like draws a figure on a piece of paper and then like closes it and then puts like a pencil.
Yeah, there is this literature on time machines as opposed to time travel, and I don't really know too much about it. But I know, I know it looks hard.
Well, it's
so you can
more than that, right? I mean,
remember Tipler had a thing where if you had a infinite cylinder, so if you aligned all these neutron stars in a kind of big cylinder and they're all rotating the same, then that would bring about those time-like curves.
I don't think that's technically right. I mean, there's this famous among the small group of people who do this paper called "Take a Ride on a Time Machine" by John Ehrman and Gordon Belloc. There may be somebody else on the paper, and they asked the following question. So there are solutions to general relativity that have closed time-like curves, but they're just put in by hand, or put in. You put them in because you're asking, can I solve these equations? Do any of the solutions have this particular feature, right? But then you can ask a question, well, suppose I'm in a universe where up until now there are no time-like curves. Can I then do something, right? Go into a lab, build something, create something that would cause there to be closed time-like curves? And as I recall, the conclusion from their paper, which surveyed a lot of the physics literature and looked at some of the technical mathematical issues, was just no, at least not in general relativity, that you can't build a time machine in that sense. There could be, this would be a view that says there could be time travel, but if there is, there is. If there isn't, we can't do anything about it.
Yeah, I think there's a lot of very technical debate there. Yeah, I know, up the street, J.B. Manchak has, theorems, and then there's theorems the other way, and I don't know. But it doesn't look like it's something easily done.
One of the earliest, by the way, contributions of philosophers to this whole literature was, Craig mentioned that one of the solutions with closed time-like curves was produced by Gödel for Einstein's birthday present, oddly enough. But anyway, produced by Gödel. And so everybody knew there was this solution. But to go around in this circle, you actually couldn't just drift. You really needed to accelerate. Okay, you needed to have a rocket with an engine to push you around one of these circles. And David Malamud actually did a calculation of how much fuel you would need to get in a rocket. If you happen to live in Gödel's universe, to get in a rocket and actually travel around one of these things. And he found that you'd need so much fuel that it would distort and destroy the entire solution because the gravitational mass of the rocket would mess everything up. So it actually turned out to be practically impossible. Even though there were time-like curves, it would be practically impossible for a person to go along them.
It turns out time travel is possible, but it's just too expensive. If it's like $5 a gallon.
Well, I have
another thing to mention, Robinson, that often doesn't come up is that's a challenge for time travel is that is the direction of time, thermodynamics. I mean, so if you went back, how is this going to be compatible with second law of thermodynamics, where you've got entropy increasing all the time. Is it gonna? Well, logically, you could imagine like putting the world on a cylinder, rolling things up, having a gas expand, and then around the cylinder come back. And so there's not a kind of logical contradiction between the two, but it's not obvious how you're gonna, send a macroscopic object like you, Robinson, back in time and have that be compatible with the second law of
Well, I have one last time travel question before we finish, and I think it should be pretty quick. But my favorite time travel movie, when I think about it, is probably not a good movie at all. It's just time and place that I saw it when I was a kid. But it's H.G. Wells' Time Machine with Guy Pearce. And in that movie, he does go to the past to try to prevent his girlfriend or fiance from dying. But the crux of the movie is that he gets in a time machine and goes to the future. But we haven't talked about time travel to the future at all. Is there a reason that we haven't? Is that more?
We're doing it all the time. It's not interesting. Right now, we're all older than we started this thing. We've been traveling through time during this conversation into the future. Now, you might want to get further into the future. I would suggest just cryogenesis. I mean, I would just, figure out how to freeze yourself if you really want to see the distant future. Maybe you can freeze yourself and thaw yourself out. That seems practically much easier to do than anything really fancy. But time travel to the future is trivial. It happens all the time. So what's there to talk about?
Yeah, if you think of like the twin paradox, the twin who leaves comes back and, they're younger. Just go a little faster, go a little further, and you get...
Well, they're younger than the twin, but they're older than when they left.
Yeah.
Both twins are still aging toward the future.
Yeah. Well, they're...
his only advantage is he can, make fun of his twin. But
Well, I mean, I don't want to push this because we have to finish, but there is a sense of time travel to the future that isn't as trivial as you're making it sound. Like, I mean, if I want to jump 2,000 years into the future and grab some future weapon or something, and then, I mean, this would entail also for my story jumping back to the present. But
it's the second part that's bad. As I say, you want to go into the future 2,000 years and see what the weaponry's like. Find one of these people who freezes people, right? And is actually pretty good at thawing them out as well. That's the hard part.
Right.
You can probably pay them and they'll give it a shot, right? They might be able to put you in stasis and thaw you out in 2,000 years, and you can look around and see what the weapons manufacturing industry has been up to. That's within the realm of possibility for sure. That's physically possible.
I mean, you're right, Robinson, that, it might be that, maybe like after the podcast, you go and you've got a closet, and the closet is actually a mouth, a wormhole mouth, and it ejects you at some point really far for in the 2,000 years in my future. But in a sense, it still is sort of, as Tim is saying, because it just means that space-time is weird and it's got a kind of wormhole to it. But in some sense, it's still the twin paradox happening.
Okay. Well, Tim, you had a pitch of sorts that you wanted to make before we finished about the Institute.
Yes, I do want to make a pitch. So for anybody who's stuck through this whole thing, we have to assume you're interested in the foundations of physics. And we are the John Bell Institute for the Foundations of Physics, of which I am the founder, and Craig is on the faculty. We are in the middle of trying to raise funds to buy the place we want to set up permanently. And so if you're interested in this stuff and you want to help us out and you like this kind of discussion among both philosophers and physicists and mathematicians, our plan is to get everybody together in a place where they can talk. We have a GoFundMe. You could go to www.johnbellinstitute.org or put in GoFundMe and John Bell Institute. And if you send us anything, we will be quite grateful for it. So just, I need to mention that because we're doing that right now, and we're in a kind of do or die situation to get this done. So hopefully, some people might help us out.
Mm-hmm. Well, I will absolutely mention that in the introduction as well for those people who don't make it 2 hours through. Though I think that this was great, and most people who get 10 minutes in will get through the entire way. But as always now, both multiple time repeat guests in my section of the multiverse. Thanks, Craig, and thanks, Tim, for joining me for this conversation.
Thanks to both of you. It was a lot of fun.
Yeah, it was really great.
Hold on, Geeslings. Before you go, please like, subscribe, follow if you haven't already. Smash all those buttons. And also, if you haven't followed me on Twitter at Robinson Earhart, or if you're not joining me every morning as I eat my pint of ice cream on Twitch at Robinson Earhart on Robinson Eats, please do so.